Okay, so I will be teaching stereochemistry and reactive intermediates. And you in this course, you have 4 blocks. So block 1 and block 2 consist of stereochemistry, and block 3 and block 4 consist of your reactive intermediates. So today we will start with your stereochemistry. And stereochemistry, you know, this is the chemistry of your mostly the stereoisomers. So what are the stereoisomers? Again, first we should know what is an isomer. So if the compounds have same molecular formula, then we will say it as your isomers if it has the same molecular formula. If again these isomers, when these isomers have the atoms connected in the same order, if it is connected in the same order, then yes, those are your stereoisomers, because they are in the same order, just their spatial or their orientation in space is different. But if it is they are not in the same order, then that would be your constitutional isomerism. Then again, your stereoisomerisms or stereoisomers, can the compounds be interconverted? Means one compound can be interconverted by rotation about your single bonds. Then there comes our conformational isomerism, if they can be interconverted by rotation about single bonds. If they cannot be interconverted, means one isomer cannot be interconverted to the other isomers by the rotation about single bonds, then there comes your configurational isomer. Again, this configurational isomer is again of 2 types. One is your geometrical isomer, one is your optical isomer. Your geometrical isomerism is due to the restricted rotation, there comes your cis-trans isomerism. And if there is no double bonds, then there comes your optical isomerism. That means these isomers are actually optically active. Then if again these are of 2 types, one is diastereomers and another's are your enantiomers. So in this class we will deal with lots of conformations as well as your enantiomers and diastereomers, mostly configurational isomers and conformational isomers. So before going further to your configurational and conformational isomers, let's see how these organic molecules, actually these organic molecules, we know that carbon is tetrahedral, that means it is in a 3-dimensional molecule. But how we do it or how we represent it in a 2-dimension, that is in the plane of a paper. So there are many representations. One is your flying wedge representation, in which if you see this plain blue lines in this molecule, you see the plain blue lines, we see that this is in the plane of the paper. And the hydrogen, that is your solid wedge line, that is the bond towards your observer, and that is the dashed wedge, which is the bond away from the observer. We can write it in both the direction, like in this molecule, in this way I have bent it towards left, and in this one I have bent it towards right. So this is your flying wedge representation of methane, the first one, and this one is your lactic acid. Okay, we can also represent it in this way, that is your zigzag fashion, when we have lots of carbon centers. In a zigzag fashion we write it, but we do not like here we should have your carbons, and we do not put our hydrogens also here. That means if this OH is up the plane, that means hydrogen would be down the plane. Okay, so this ink representation is also coming. Whatever I am writing is coming.
Yes, ma'am.
Okay. Okay, so we can write it in a zigzag manner. So if as we do not represent hydrogen here, but still there it is there, and carbons like this joint carbons are also being not shown. So this is your flying wedge representation. Also we can do your Fisher projection. In your Fisher projection, there are 2 types of Fisher projection. This one is our Fisher projection formula. So from your flying wedge, okay, so you just see the central carbon atom is lying on the plane of your paper, and this waste A and B, they are just coming going backward of the paper, and C and D, they are just coming out of your paper. Or we can just represent in a Fisher projection where you have one vertical line and one horizontal line. And in this case, the horizontal line, the C and D, okay, these substituents, carbon is in the center, okay, and the C and D are these substituents are lying in the plane of the paper, and A and B, one is going A is of the plane of the paper, or that is towards the observer, and B is away from the observer. The below is your away from your observer. Okay, also we can write it in a Newman projection as well as in a Sawhurst projection. In a Sawhurst, this is the staggered conformation of your Newman projection, in which we are seeing through the carbon atom. Okay, we are putting all these suppose we have two carbon centers, and we are seeing it through this and putting the other carbon just back of it. So that gives you a staggered conformation. I will come to what is your eclipse conformation also. And in case of a Sawhurst representation, we put it a diagonal line, and here it gives you the better actually spatial relation of the substituents. So Sawhurst presentation is, again, we have staggered conformation as well as your uh, eclipsed conformation. So in your staggered conformation, this is the staggered conformation. If you see this CS3 group and this CS3 group, they are just away from each other. But in this case, they are just on the same side, or they are just their dihedral angle is zero there. Okay, so how these projection formulas are interconverted, Fisher to Sawhurst and Sawhurst to Fisher, or from Newman to Sawhurst, you can go through your book or some of, or the through models. Actually it is easier to explain, but still you can just see, I am just showing one. So first you see the A, in which we have this carbon is our front carbon. So to present in a Sawhurst projection formula, first we write this diagonal line like this, and the first carbon, carbon 1, is present here, and the bromine in Fisher projection, that is on the left hand side. So I have put it bromine on the left hand side, and hydrogen is present on the right hand side. Again, and the fourth carbon, we first do it in your, from Fisher to first we go for the eclipsed conformation, eclipsed. And so the CS3 and this CS3 on the same side. So CS3, that bromine, CS3 left side, here your hydrogen and bromine. Then you just rotate it. While rotating, you just keep this front carbon fixed and just rotate 180 degree. When you rotate it in through 180 degree, you see this CH3 was here and it has gone to the this position, and again hydrogen was here, it come to this position. So now this is a staggered conformation. I think from BSc you know what is staggered and what are eclipsed. Okay, from this you can just see the staggered and eclipsed conformation. You, from the Newman projection, you see phenyl and CH3 groups. These are staggered in an eclipsed way. Okay, so like that you can just do from Sawhurst to Newman, and from Newman to Fisher projection, or vice versa. You can just do or interconvert your projection formulas. So next comes your symmetry elements and symmetry operations. What are your if by rotation or by plane, if you are just getting the same molecule, then that is your symmetry element. So suppose in this molecule, if you see, if I rotate this dichlorocyclobutane through 90 degree, through 90 degree, so we will get this one. But again, if we again rotate it through 90 degree, so we get the same molecule, we get the same molecule. So we can just say that by rotating the first molecule, the initial this one, by rotating it through 180 degree, we are getting the same molecules. So that means you have a two-fold rotational axis of symmetry. Similarly, if you see this molecule here, we have a plane of symmetry. Means if we just put a plane mirror here, this half is exactly the exactly equal to the other half. So that is known as your plane of symmetry. Similarly, we can have different type of plane of symmetry: horizontal plane of symmetry, and that is diagonal plane of symmetry, and diagonal plane of symmetry, and again your uh, just vertical plane of symmetry. You have three different types of plane of symmetry. Again, you have a center of symmetry also present in a molecule, some molecules actually. So what is center of symmetry? Suppose you start from this CH3 group and you are passing through a point, and you are actually experiencing the same distance when you go to another just opposite, there is another CH3 group. So you are just going through this center, and the distance is same, and you are again approaching, or you are reaching a group which is same as that. So you have a center of symmetry, that is known as your center of symmetry. Next is your alternating axis of symmetry. Alternating axis of symmetry is, first you rotate a molecule through um, through some angle, and then if you just take its mirror image, and if that is equal to the initial, means before rotation. Hello. No, I am busy now. Actually, I have a class now. So can you do it afterwards? No, no. After 8:30. After 8:30, I will call you. Yeah. Yeah. So here, actually, if you just see this molecule, we have rotated it through 90 degree, and if you rotate it through 90 degree, and then just make a mirror image of this one, then we will get the same molecule. So this is having a fourfold alternating axis of symmetry. So what are the symmetry designations for your chiral molecule? So chiral molecule is, which is like actually which rotate, means which are optically active, and there is that is attached to four different centers. We will come one by one some many examples of chiral molecules. So its first symmetry designation is, if there is any alternating axis is present, and then that would be inactive. Alternating axis of symmetry and center of symmetry, if it is present, then that molecule would be optically inactive. And when there is alternating axis is absent, but you have a rotational axis, any simple rotational axis is present, then that molecule is known as your disymmetric, and these are usually optically active. And when you do not have any alternating axis of symmetry, and also any simple axis of symmetry, then those are known as your asymmetric, and those are also usually active. So what is optical activity? Optical activity is when it rotates the plane polarized light. So what is plane polarized light? We all know that our normal light, it consists of actually electric waves as well as your magnetic waves, and they are actually directed or oriented towards everywhere, actually all towards all through every direction. But when we pass it through a plane polarizing filter, that gives you a plane polarized light. So what does the chiral molecules or this optically active molecules do? Suppose these two are use the C. If this is L-alanine, this is your D-alanine. They are just the mirror image of each other. So these two are enantiomers. So if one rotates your plane polarized lights to clockwise direction, the other one will rotate the plane polarized light to your anti-clockwise or counterclockwise directions. So enantiomers are structures that are not identical but are mirror images of each other. And structures are chiral if they cannot be superimposed on their mirror images. Like your left hand and right hand, they are not mirror images. So your left hand glove never fits with your right hand, or right hand glove never fits with your left hand. But if you just see these two chairs, there is your plane of symmetry, so they are superimposable on its mirror image. Even your letter A is symmetrical, there is a uh, symmetry. Even letter 8 also, there is a plane of symmetry. So if a molecule contain one carbon atom carrying four different groups, it will not have a plane of symmetry and must therefore be chiral. So first condition, if we have a carbon and that is attached to four different groups, so that would be a chiral center. We will come again that there would be some actually deviations from this, but there are some conditions. Okay, so these are your some chiral objects, and these are your achiral objects, or the enantiomers are non-superimposable mirror images of each others. So how we write or how we give the notations to these enantiomers? So that is your configurational notations for optical isomers. So first system is based on your DL nomenclature. Okay, here I just forget. So when it is in the clockwise direction, when the enantiomer rotate the plane polarized light in the clockwise direction, we note it is as plus or dextro-rotatory. Dextro means it is in the towards right, and minus if it is levo. and these are represented as small d and L. But actually, while we are writing this DL system of nomenclature, we are writing capital D and L. So this is a relative nomenclature. Actually, this glyceraldehyde is first given L and D. So those were, this glycerol was glyceraldehyde because it was dextrorotatory, and this glyceraldehyde was levorotatory. So based on this, they have just named some other groups or other compounds as D and L. So what is in D-glyceraldehyde? If you just see the Fischer projection, OH group is on the right, and in L-glyceraldehyde, the OH group is on the left. So in any enantiomer, if the OH group is on the right hand side, then that would be your D form. And if the OH group or any this kind of group, suppose here we do not have a NH group, OH group, but we have a NH3 group, but this is towards your left in the Fischer projection. So those will be named as your L isomers. And here, don't get confused. You see, this is D plus glyceraldehyde, but this is D minus lactic acid. So D is just its configurational notation, but minus means it rotates the plane polarized light in anticlockwise manner. So this is the DS system of nomenclature. So this is a relative configuration nomenclature, because we are just relating to D and L glyceraldehyde as the standard, and then putting the configurational notations for other molecules. So to overcome this, there came one, your RS system, which was put forward by Can, Ingold, and Prillag. So this, here there are some rules. So first, rank the atoms in RS system of nomenclature. First, rank the atoms to chiral center according to their atomic number. So we know that having bromine is having higher atomic mass as compared to, so here we have four substituents: bromine, chlorine, methyl, and hydrogen. So bromine is having higher atomic mass as compared to chlorine, as compared to carbon, as compared to hydrogen. So in this way, so you just prioritize according to your atomic number. So rotate the molecule such that substituent ranked 4, which substituent ranked 4 is in the back, that is in the dashed line. Okay, so here we already have hydrogen in the 4. So if we uh, trace the path from 1 to 2 to 3, if it is clockwise, then it has write it R. So if we trace the path from 1 to 2 to 3 in a counterclockwise manner, then it would be assigned as S. So again, in this case, you just see here our this ethyl is okay. Here all are carbons. So in this case, you have to see how many carbons are attached to which substituent has more carbon centers. So in this one, you have 1, 2, 3, 4. So here you have more number of carbon centers. So this will get more priority. And in this case, you have 1, 2, 3. So that will get second priority. And here you have only 2, so that will get the third priority. And in this is only methyl, so one carbon. So this is your priority number 1, 2, 3, and 4. But in this case, the lower priority CH3 group is not in the your dashed line, that is in the front. So what you will do, actually, just in this case, you just see how it is going from 1 to 2 to 3. So this is going anti-clockwise, so this should be S. But as it is not in the back, or it is not in the waistline, this is actually the simplest way. Normally you have to swap the substituents twice, then do it. But this is the easiest way. First, you just check the lowest priority group is on which side, if it is on the top, or towards, or it is backwards. If it is backwards, then there is no problem. When it is just up, or that is in the front, then in that case you just do it S, then just swap it, or just uh, give the opposite one. So it is one, as CH3 group is on the front, so it is actually giving us S, but if as it is in the front, it would be give us R. Okay, so now here you just see, here the hydrogen is again on the horizontal way, or it is on the solid star. So here also you can just see we have which one will get more priority, because first carbon atom attached here is chlorine, so that would be priority number 1. Here the second, here carbon is there, bromine is also there, and in this carbon you have carbon and oxygen. So bromine gets more preference as compared to oxygen. So this will be priority 1, this is priority 2, and again this is priority 3. So it is actually 1 2 3, it is going uh, in a clockwise manner, but as hydrogen is, or our the lowest priority is on the front, in the front, so in that case we have to just reverse the result, so that would be S. So we can have many examples like this. So in this case also, suppose that is not in the front or not in the back, but it is in the plane, in the page. So in that case, what, like in this here, so hydrogen is in the plane, not on the solid or dashed wedge, so it is on the plane. So what you do, just swap this hydrogen, whichever group we have, on the actually dashed wedge. So here CS3 is on the dashed wedge, so you just swap the position and then you just give the priority. We know that chlorine is more, atomic number is more as compared to oxygen, so that will come as the first, oxygen, then it was carbon. So in this way this appears to be your R, but here we have done only one swap. You should do two swaps, so only one swap, so it appears to be R. As in that case you again swap the result, so R should go to your S. So these are the easy ways to give the notation, RS notations to your chiral centers. So or in your Fisher projection also you can do like this. In this case you have to see whether the hydrogen is in a vertical line or in your horizontal line. If it is in the vertical line, whatever comes, that would be the result. Like you see, chlorine is your first priority here, and the ethyl group is your second priority, and methyl is your third. So here it goes from, while tracing from first higher priority to lower priority, it goes in a clockwise direction. You don't have to bother about four, you just have to 1 to 2 to 3, you have to trace from 1 to 2 to 3, so that is clockwise or R configuration. But in this molecule, if you see, the hydrogen is in the horizontal line, so here you just have to do trace 1 to 2 to 3, whatever is again R. But as hydrogen is not on the vertical line, it is on the horizontal line, just reverse the configuration, so it has to be S. So in a Fisher projection formula, if you just do the 180-degree turn, if you projection formula, if you turn the projection formula 180 degree, then that configuration would be retained, but 90-degree would give you the enantiomer. So 180-degree turn would give you the same compound. Or if you just first, you just see you switching CS3 and Br, and again, so double swap, if you do the double swap, it would give you the same configuration, but single swap would give you a different configurations. Okay, this RS notation and DL notation are actually in your stereochemistry too, but actually I think this one is necessary here, because we are going to see all these notations in our this today's class, so I just incorporated it here. Okay, so you can just assign RS notations to these molecules also. So as you see, this one will first priority, this one would be second, this one would be third, fourth. Okay, our fourth, that is already in the, actually already in the vertical line, so it is clockwise direction, so that would be R. But in this case, this one is first priority group, this one is second, uh, this one is third, and this one is fourth. So here if you just see it is going this direction, but clockwise, but here your hydrogen is in your vertical position, so it should be R, but you have to reverse it, so this would be S. And in this case, here you have, this one is first priority because you have a bromine, after carbon you have a bromine, then here you have two carbons, but here after carbon you have again another two carbons, so this one is going to be second priority, this one is going to be third, this one is going to be fourth. So here our fourth, that is the lowest priority group, is already in the vertical position, so while we trace from 1 to 2 to 3, that is in anti-clockwise direction, so this would be assigned S. So okay, so what enantiomers are actually the mirror images of each others. So what about up to now we have just seen only one chiral centers are there. So when we have two chiral centers, as you can see, we have a chiral center here as well as here. So this isomer, this one and this one, they are mirror images of each other. And again we can also write it in this way: this one and this one are mirror images of each other. But if you just see 1 and 3, they are not mirror images, but still they are stereoisomers. So these two are enantiomers and these two are your diastereomers. Even this one also diastereomers, because they are not mirror images. So but they are also stereoisomers. Means enantiomers have the, you can just see they have the same chemical properties, but diastereomers will have different chemical properties. Okay, so diastereomers may or may not be optically active, and if uh, here they are optically active, we will see some diastereomers which are not optically active. And there are different diastereomers also, like you just see they can be chiral or achiral. If you just see, this is a in this molecule there is a plane of symmetry. Okay, so these two are diastereomers, but still they are not chiral because there is a plane of symmetry. But here this uh, enantiomers are, you get this, that enantiomers are mirror images of each other and they are non-superimposable mirror images. But diastereomers are stereoisomers which are not uh, mirror images of each other. uh, Even here also, if you just see this 2-bromo 3-chlorobutane, 1 and 2 are enantiomers and 3 and 4 are your enantiomers because they are mirror images of each other. But 2 and 3, they are diastereomers. Even 1 and 3 also diastereomer, 1 and 4 also diastereomers, and 2 and 4 are also diastereomers. They are not mirror images of each others. If you just see, you can just do the arrays notation here. You can just see one would be R or S. So only you just consider this one. Here, these two are enantiomers. So they are perfectly mirror image of each other. S mirror images R mirror images S. But here, SS and RR. So these are also enantiomers. But what about this molecule and these molecules? Here SR and this is SS. To go from one enantiomer to another, both stereogenic centers are inverted. But to go from one diastereoisomers to another, only one of the two is inverted. So next comes our meso compounds. Like some diastereomers are not chiral actually. So we will consider the stereoisomers of tartaric acid. So you just see in this case, you have both the end groups are same, COH, COH. So in case of tartaric acid, these two forms, 1 and 2, they are mirror image of each other. Again, 3 and 4 are mirror images of each other. So these two are enantiomers and these would be your diastereomers. Okay, because they are not mirror images. And these two are optically active. These enantiomers are optically active. That means they rotate the plane polarized light. What about these two? They have chiral centers, but still they are not optically active. That is, these compounds are known as your meso compounds because you have a plane of symmetry. The upper half is exactly the opposite or exactly the mirror image of the lower half. You just see there is a plane of symmetry. So these compounds are achiral, although they have your chiral stereogenic centers, but they are achiral. These compounds are known as your meso compounds. So meso compounds are optically inactive due to the internal compensation. Internal compensation. Because if this half will rotate the plane polarized light to in this direction, the other one will rotate the plane polarized light in the opposite direction. So they are optically inactive. That is known as your internal compensation, because the other upper half is exactly the mirror image of your lower half, or there is a plane of symmetry. So these compounds are known as your meso compounds. What is racemic mixture? Up to now, we know that we have enantiomers. Enantiomers rotate the plane of polarized light in opposite directions. So if we have two enantiomers in equal portions, then the one half would uh, rotate the plane of polarized light towards your anti-clockwise, the other half would rotate the plane polarized light in clockwise direction. So the net result would be there would be no rotation of plane polarized light. So those, that is known as your racemic mixture. So this is due to your external compensation. The other, this one meso compounds, here you have internal compensation, because here the inactivity, optical inactivity is within the molecule. Means there is a plane of symmetry in the molecule, so there is internal compensation. But in this case, when we have two enantiomers, okay, two enantiomers, when they are mixed in equal proportions, so there would be uh, there would be no rotation of your plane polarized light. So you just see in this case our 2-butanol, when this R2-butanol will rotate the plane polarized light in this direction. Again, the S2-butanol will rotate it in the opposite direction. So there would be no net rotation. If we have unequal contribution of your enantiomers, that is not equal contribution, equal, one enantiomer 50, another enantiomer is not 50, or one is 60/40, then we would have a rotation, but that not be equal to your rotation, but is due to your pure enantiomer. So how these racemic mixtures are formed? So these racemic mixtures are formed by mixing a pair of enantiomers in equimolar ratio. So if we do the 2-S-butanol and R-butanol, we add it in equal amounts, molar ratio, same molar ratio, 0.5 mole and this 0.5 mole. So that would give you a racemic mixture. Also, we can get a chiral production of chiral center from an achiral compound. Suppose this hydrogenation of pyruvic acid, that gives you lactic acid. So this one would give you a plus and minus lactic acid, because here we are not taking any chiral compound, chiral reagent or something, so that will end up having your racemic mixtures. Or any hydrogenation of your this carbon carbon double bond, that also give you equimolar ratio of R and S. Then comes some chiral catalyst, if comes, then one will be preferentially formed, R will be preferentially formed over S, but that needs some specific catalyst. But just in the normal condition, you would get a mixture of R and S. Again, racemization. You can do racemization, means if you have a chiral compound, enantiomerically pure compound, you can do the racemization. In this racemization process, suppose we just do the acid catalyzed enolization of this this ketone. So, in the process of enolization, you see this hydrogen is going to this carbon carbon double bond. So now the formation of phenol is achiral. So as it is achiral, now the OH group, again this will again come back, and when it comes back, the hydrogen can add to this phase of the carbon or this phase of the carbon, so resulting in the formation of both the enantiomers. So that starting from one enantiomer, you are getting both the enantiomers, or you are getting a racemic mixture. Similarly, in case of your SN1 reaction, you are starting with one enantiomer, that is a substitution reaction, enantiomer reaction. It passes through a carbocation intermediate, so where there is equal possibility of attacking of the nucleophile from both the sides of the carbon, resulting in the formation of both the enantiomers. So that leads to a racemic mixture. Next comes your separation of your racemic mixture, that is also known as your resolution. So resolution means you are separate, if you have a racemic mixture, you are separating it by different methods. So some methods are there uh, in your study material, that is your mechanical separations, which I have not given here. Actually, mechanical separations are when you have solid enantiomers and they crystallize in different shapes. So one enantiomer would be in a one enantiomer would be a like different orientation, the other enantiomer would have a different orientation in crystal forms. So using your magnifying glass, you can just pick the enantiomers. So that is very difficult, and that is applicable only for very limited enantiomers. So next one is your resolution with enzymes. Actually, we know that enzymes are our biocatalyst, which selectively, they are very selective, they are very specific, they just reacts only at a specified reaction. So if we just take this This is our racemic mixture. Whenever we write a racemic mixture, we either write plus minus or we write DL. That means we have both the enantiomers or racemic mixture. So plus minus insect pheromone, when it is treated with your Pseudomonas cassia lipase, which is an enzyme that only reacts with your um, this enantiomer, okay, that reacts only with this enantiomer. So this is just a ester to alcohol, and the other enantiomer is remained on reacted. So now you can just if separate these two, and if you want this one back, then you can just actually make esterification reaction here again. So this is your resolution with enzymes. You can do other chemical methods also. Again, formation of a diastereomeric salt. As we know that diastereomers differ in their physical properties, their melting point and physical point. So if we just convert the enantiomers into diastereomers, then it would be easier to separate them, because enantiomers don't differ much in your uh, melting point, or their chemical properties and physical properties are almost similar, same. But that if we convert it to diastereomers, then you can just separate it. Suppose you just see, if you have enantiomers of R acids and S acids, when you use a base who has a uh, um, who which one is your S base, means that's stereochemistry, or that's configuration is S. So now this R acid combined with S base to form a RS salt, and S acid combines with S base to form a SS salt. So RS and SS, they are diastereomers. Enantiomer would have been if RR and SS, they are enantiomers. But RS and SS, they are your diastereomers. Now they can be easily separated. So once your diastereomers are there, you can just easily separate them through many means are there. And again, you just treat it with acid to get your R acid and S acid. So that is your formation of your diastereomeric salts. Again, there are also chromatographic separation. So you, chromatographic separation, it relies on the difference in affinity between a stationary phase. Actually, we always put a stationary phase or column like thing, okay, where we have a stationary phase, and we have a mobile phase in which you have solvent traveling through the stationary phase. So there would be relative affinity for your stationary phase. The mobile phase will have a relative affinity for your stationary phase. So which one would be having more affinity, that will pass through the stage, or that will travel slowly, and which has less affinity, that would pass uh, fast. So first, actually in a stationary phase, that would has to be a chiral stationary phase. So in that one, we put the racemic mixture is loaded or put in on the column, and then suppose this has a more affinity for S. This chiral stationary phase has more affinity for your enantiomer S. Then that will move slowly, and this R enantiomer will move fast. So now R enantiomer would reach the bottom of the column first. So you collect it. Then after all the R are gone, means you can just determine it from ORD if it is coming, or there would be different techniques to measure. And again, after you finish collecting R, then you can collect your S. So that is your chromatographic separation of your racemic mixtures. There are also kinetic methods. So in kinetic methods, some enantiomers, like suppose we have two enantiomers SR and SS. So in this case, if you just see SR, the rate of reaction is very fast, and SS, the rate of reaction is very slow. In that case, what you do, you just treat with some enzyme or something, so in which one enantiomer is very fast, so that will be ac- acyl uh, acetylated, so that would, as this one is more reactive, that would be acetylated, and the other one would be unreacted. So you can just uh, get a pure enantiomer, and this, if you want the enantiomer back from this, you just do the hydrolysis, and again you would get your this enantiomer back. Okay, so this depends on the relative reactivity of your enantiomers. If one enantiomer is there is its rate of reaction is slow, and then that won't react, and which one is faster that would react to give your product, the other one will remain as the pure form. So criteria of optical purity. So what is your optical purity? Means if we have a mixture or a mixture of enantiomers, then we can just find out your enantiomeric excess. Now in your asymmetric catalysis or in your chiral catalysis or any chiral asymmetric reactions, enantiomeric excess is a actually main important point. What is enantiomeric excess? If we are taking, like in your reaction, there is chances of getting two enantiomers. So which enantiomer we need and how much excess it is from the other enantiomer. So enantiomeric excess is your excess of a single enantiomer divided by your entire mixture into 100%, or we can just say moles of one enantiomer minus moles of the other enantiomer divided by total moles of both the enantiomers into 100. Or also we can just calculate it from our experimental value. We just get a specific rotation, like I have just told how much rotation we are getting from your optically polarized light, how much rotation. So observed specific rotation divided by specific rotation of the pure enantiomer. So pure enantiomer will have a specific rotation, suppose it must be like this. So if we have some impurity, then it would be less. So in that case, observed specific rotation divided by specific rotation of the pure enantiomer into 100. So that is your percentage enantiomeric excess. So till now, anyone is having any doubt? Till now, anyone is having any doubt? Okay. Okay. Okay, then we will go to other part. Next, this completes
मैम
actually your
मैम
unit. Yes.
मैम जो
Yeah.
प्रिपरेशन ऑफ रेसेमिक मिक्सचर जो है ना,
हाँ हाँ
तो उसके जो प्रिपरेशन में थोड़ा सा डाउट था।
हाँ, बोलो क्या डाउट है, किधर?
जो आकारेल है
ये
मैम, जो
अच्छा।
आकारेल जो अच्छी तळटा प्रोडक्शन ऑफ ए कायरल सेंटर फ्रॉम एन आकारेल
हाँ
कंपाउंड आकारेल टू पीडीसी पैलाडियम और
अच्छा,
कार्बन
हाँ
का जो
ठीक
मिक्सचर
अच्छे
है।
बुझुଛି। ଦେଖ ଏଠି ଆମର ସପୋଜ ମୁଁ ଗୋଟେ ସିମ୍ପଲ ମଲିକ୍ୟୁଲ ନେଲି CH3 CO C2H5. So this is an achiral molecule karan ethi charita ethi ketata substituent achi, we have three substituents, okay, in this
हम्म,
carbon. So this is an achiral compound, this is not a chiral compound. When we do the hydrogenation, okay, so we are generating a chiral center, OH and H, carbon oxygen double bond. We are incorporating or adding hydrogen across the carbon oxygen double bond. Okay, so in this case we are getting a chiral molecule. So we are generating a chiral center here, but the hydrogen has equal chance of attacking from this side or also from the this side, because we are not taking any chiral reagent. So that would give us two chiral centers. R and S are equal probable. You got it?
यस मैम, यस मैम।
Yeah, you are getting a chiral center. You are producing a chiral center from an achiral compound. But in this case,
मैडम
actually the
कायरल सेंटर कार्बन सेंटर जो जहाँ
chiral
चारिपटे
center
चारटा
ଏଥିପାଇଁ
अलग अलग
କହୁଛି
फंक्शन।
କାରଣ ସେଥିରେ ହଁ କାଇରାଲ ସେଣ୍ଟର ମାନେ କାର୍ବନର ଚାରିଟା ଅଲଗା ଅଲଗା। ମୋଷ୍ଟଲି ଆମେ ଯେତେବେଳେ ମୁଁ ଏଇ ଯେତେବେଳେ କହୁଛେ ଷ୍ଟେରିଓ ଆଇସୋମର୍ସ ଅର୍ ଯେତେବେଳେ ଆମେ କାର୍ବନରେ କହୁଛେ ଟେଟ୍ରାହେଡ୍ରାଲ କାର୍ବନରେ ଚାରିଟା ଡିଫରେଣ୍ଟ ତମର ସବଷ୍ଟିଚୁଏଣ୍ଟ ଯଦି ଲାଗିଛି, ଦ୍ୟାଟ୍ ଇଜ ୟୋର କାଇରାଲ ସେଣ୍ଟର। ଓକେ,
ओके
or
ओके
that
मैम।
is also known as your stereogenic center. Okay, any other doubt?
मैम सेपरेशन टिके आउथरे।
Separation ro artha hela you are separating because actually whenever you are doing any synthesis you are getting a racemic mixture. Okay, we always need a single enantiomer. If we just don't, means most of our medicines, or levocetirizine we are eating for our levocetirizine we are having for cold and cough, that is your anti allergic,
आज्ञा आज्ञा।
anti-allergic medicine. So you need it in means a pure form. If you don't have the pure form, then that efficacy will diminish, or in some cases you will get some other side effects also. So for that reason, you have to separate one enantiomer from the other, because in the reaction mixtures, if you are not doing any chiral environment reaction in any chiral environment, then you are not getting any means enantiomer, pure enantiomer. So in that case, you can just separate the enantiomers in many methods. In your book, there is one mechanical method is there. You can just, if you have crystals, okay, crystals means that should be a solid. So if you have crystals and both the crystals means this enantiomers crystals look different from the other enantiomer crystal, then you can just hand pick them through a magnifying glass. Okay, that is one method, but it's not very feasible because all enantiomers don't form crystals. Okay, next you can do resolution. Resolution means you are separating racemic mixtures using enzymes. Enzymes are our biocatalysts. Okay, they have affinity for a specific enantiomer. Okay, in this plus minus insect pheromone. So suppose PCS has a specific affinity for your S enantiomer. Okay, that will react. The S enantiomer will react. The other enantiomer will not react. Our enantiomer
Other
react.
enantiomer will be dormant.
That will be dormant. That won't react because that will not attack him. It does not
Okay.
have affinity for that one, so it won't react.
Okay.
So you will get the pure of this one, pure form of this one, and this one will react.
So
Okay,
can so you can easily separate it.
yeah, you can easily separate it. Next is formation of your diastereoisomeric salt. I have already discussed what are your diastereomers. Those are not mirror images.
Mirror
Okay,
images.
they're not mirror. Enantiomers are mirror images, but diastereomers are not mirror images.
They are
And what
also
is
optically inactive.
they may be optically inactive, they may not be optically inactive. Okay, if
Okay.
you just see this, I have just here you see this 2 bromo 3 chlorobutane, they are optically active. Okay, they are
Hmm.
optically active.
Active.
And these two are enantiomers, but this one and this one relation here and here, these are diastereomers. Okay,
Okay.
some diastereomers may be optically active or may not be optically active. As here, these diastereomers are not optically active. This mesotartaric acid, they are not optically active because they are, you have a plane of symmetry. Here you do not have a plane of symmetry. If you just see, you have bromine here, you have chlorine here, so you do not have a plane of symmetry here. So this one is optically active. So
Okay.
when you form diastereomers, that when you are forming a diastereomer, when you have more than one chiral center, you have more than one chiral center. So relatively, you are getting enantiomers and diastereomers.
Experiments. Okay. Thank you.
So you got it.
Thank you,
So
ma'am.
now
Thank you.
once you form your diastereomers, you can just separate it by many chemical methods. Okay. So next
Okay.
year, chromatographic separation, that is chromatography related and kinetic methods. Next comes your confirm. Up to now, we have done configurations. Okay. So configurations are like what is conformation and what is configuration. Conformation is you can just rotate it through a single bond. You can get many isomers. Suppose you just take the example of yourself, you can have many conformations. You can sit, stand, sleep, run, or you can put your hand down, or uh, legs up. But if you just configuration would be if you just remove your hand and put it near the leg and remove your leg to your hand. So configuration and conformations are different. Conformations in means you can have a many number of conformers. You can just rotate it many times at among your single bond. Suppose you just see here, changing the configuration of a molecule always means that bonds are broken. Okay, a different configuration is a different molecule. Changing the conformation of a molecule means rotating about bonds but not breaking them, but it is going to be the same molecule. Okay, so suppose you just see these two configurations, these two are enantiomers, but if you just rotate here this bond, this carbon and this carbon, if you are just rotating, you are getting different conformers, but all are having the same configuration. If you just do the RS notation, all are going to give the, these three are going to give you the same configuration. But here these two are your mirror images and these two are configurations. You cannot convert one to this, but these conformations are interconvertible. Some will be of higher energy, some will be of lower energy. If you just see, this is having, this conformation of you is having less energy, but this one you would have more energy, or this one will require more energy, but this one is a stable conformer. So conformation is the spatial arrangements of atoms or groups in a molecule. Okay, so next is we will do some conformations, conformational isomers of some molecule. Actually, these are in your BSc course also. So first of all, we will take the example of ethane. So this one is the Newman projection formula of ethane. Ethane can have many conformers. Actually, you can rotate along the carbon-carbon bond n number of times, but some will have your lowest possible energy and some will have your highest possible energy. So there are two different, actually more different conformers are possible. One is known as your staggered, one is known as your eclipsed. So eclipsed means, suppose you just see the carbon along this direction, so this hydrogen and this hydrogen is being eclipsed by this hydrogen and this hydrogen is being eclipsed by this hydrogen. You are just seeing through one carbon, and in this conformation the hydrogens are being eclipsed by the front carbon hydrogens. So you have, when you rotate this along your dihedral angle, what is dihedral angle? This is the, suppose this is your front carbon hydrogen and that is your back carbon hydrogen, this one. So the angle between this, not the same, not this angle. Okay, it is not this angle. Actually, this is the front carbon, its hydrogen, and the back carbon, its hydrogen. That angle is known as your dihedral angle. So when you first starting from your eclipsed conformation, as you have these hydrogens are eclipsed in an eclipsed position, so they would have higher energy. So when you just rotate the carbon carbon bond in your different dihedral angles starting from 0, 120 and 240, you would get a staggered conformation, then eclipsed, again staggered, again eclipsed, staggered and eclipsed. So eclipsed conformation is your higher energy conformation or less stable, and staggered is your more stable conformation. Eclipsed means it is being blocked, you can just see the back hydrogen, that is your eclipsed conformation. And staggered, you can just say it, or you can just view these hydrogens, this carbon and the other carbon is on the back, so this is your eclipsed conformation. Okay, in case of staggered, okay, in case of staggered, this one is your eclipsed conformation, this one is your staggered. You can see all the hydrogens, but here this hydrogen blocks the hydrogen in the back, that one. So next comes your conformation of butane. In N-butane, now you have, in ethane you have only 2 carbons here, so in butane we have 4 carbons. So we just see the this, okay, and you have other hydrogens here. So you just see through this carbon carbon bond. So one methyl group, okay, this one is your first eclipsed position where methyl and methyl, this methyl group is eclipsing the methyl on the other carbon. So when you start rotating it, so this comes in a this position, so this is your eclipsed position. At 60 degree you get a stagger, that is also known as your gauge. And again rotate it, this hydrogen will come towards your this methyl will come to this. When rotating, you just fix one, the front carbon you are fixing, the back carbon you are just rotating. So next comes your again your eclipsed conformation, again staggered. And then in this staggered conformation, you just see this methyl and this methyl, they are just opposite to each other, so that is also known as your anti-periplanar. They are just opposite to each other, so that is your anti-periplanar. So this is having the lowest energy, that is the staggered conformation, but that is also named as your anti-periplanar. And again if you rotate it, then it will again go to your uh, eclipsed conformation, that is anticlinical, and again that goes to your staggered gauge. So again when again you rotate it 60 degree, then it will again come to your eclipsed, which one again at your 0 degree. So in case of your eclipsed interaction, you will see that there would be maximum there would be actually more interaction between your methyl group. So that would have a more steric hindrance, so that would have higher energy in eclipsed interaction as compared to your staggered interaction. In case of staggered interaction, your methyl groups or the bulkier groups are opposite to each other or anti to each other, so that gives you a more stable conformation. So actually, if you just see, there would be the energy difference is not much the along the your staggered and eclipse, so you can just rotate it. Sometimes it would means depending on the reaction conditions, it can have a eclipsed conformer or a staggered conformer, but its main preferred conformation is your eclipsed conformation. So this is the potential energy diagram of your butane against your dihedral angle theta in degrees. So next comes your stability of your cycloalkanes. So this one is your cyclopropane, cyclobutane, cyclopentane, hexane. So actually this should be written like this, okay, in a planar form. But actually, because of this angle strain, okay, so this is your cyclopropane. So this carbon is set, this carbon is having four substituents. We know that our methane or anything that should have a bond angle of 109 degree 28 minutes, but when it is present in the cyclic form, they are actually forced to have uh, like in case of cyclopropane, this is forced to have a 60-degree bond angle. In this case, that is forced to have a 90-degree bond angle. So they are in a kind of strain. This strain is actually developed put forward by Bayer. So this is known as your Bayer's angle strain theory. So if you just see, in case of cyclopropane, it is in a strain of 49 degree, and in case of cyclobutane, you have more strain. In case of cyclopentane, there is less strain. Cyclohexane is less, and cycloheptane and cyclooctane. Although these higher cycloalkanes, that is cycloalkanes having higher number of carbons, are having more strain, but still they are more stable, which we can just know from their heat of combustion. Actually, these cycloalkanes are more stable. They do not remain in planar form. Slightly they are puckered. As you can see, this angle is almost straight, but these bonds are not straight. They are having a puckered this they are no longer remain puckered, or they are convex or concave type. You just see these are convex, and the higher cycloalkanes get actually concaved. And so cycloalkanes mostly you have your uh, conformation of cyclohexane is more important, and that is prescribed in your text in your syllabus. Actually, cyclohexane, our cyclohexane having six number of carbons. When we write it in a planar form, it is like this. So actually, this one, this form or this conformation is not very stable. Rather, it stays in a stable conformation that is known as your chair conformation. So this is the cyclohexane in a chair conformation. Why this conformation is stable? Because if you just see, this is this in this conformation, all the carbons, if you just see the Newman projections, so in this way all the bonds are fully staggered. They are not eclipsed. All the bonds are staggered. So this is the lowest energy possible. So cyclohexane is strain free. So that no longer remains in this state. This remains in the cyclic chair conformation, where there is no uh, eclipsed bonds are there. All the bonds are fully staggered. But when you can have different conformers or conformations of cyclohexane, one is your boat conformation. So in boat conformation, here you have two hydrogens. This is in the form of a boat, and you have two hydrogens here, where they are hindrance is there, so they are not very stable. And you can have a twist boat conformation, where this eclipsed interaction, this is actually eclipsed interaction, this flag step position or this eclipsed interaction is more in case of boat conformation. When you twist the boat, so you get a twist boat conformation, in which you have the this they go a bit far from each other, or your eclipsed condition is lowered. So we can say that is a bit lower in energy. So we have in cyclohexane we have different conformations. One is your chair conformation, boat conformation, twist boat conformations. So the energy profile, potential energy profile of your cyclohexane along your actually dihedral angle or reaction coordinate. So your chair conformation is the most stable conformation. So from you can write the chair conformation like this, or you can just flip it to chair conformation like this. Okay, so this is known as your chair flip conformation, flipping one conformation to other conformation, that is known as your flipping. So when you go from one conformation to other conformation, chair is flipped to half chair, again to your twist boat, to true boat, and then twist boat to half chair, again to your chair conformation. So most stable conformation of your cyclohexane is your chair conformation. Okay, in case of cyclohexane, how you write it, you have to put this two in a parallel. This one and this one has to be parallel, and this one and this one has to be parallel. I am just didn't get the okay. Again eraser is there. Okay, pen. So this one has to be parallel, and this has to be parallel, and this has to be parallel. You have to write the cycle exam, they have to be in the same plane. This okay. So here all these substituents, all the green hydrogens you see, they are all up relative to their partners on the same carbon. if, if you just see this hydrogen and this hydrogen, so this hydrogen is up, this hydrogen is down, and this hydrogen is down, and this hydrogen is up. If you just say that okay there would be steric hindrance here, no, it is not. Actually this hydrogen is up and this hydrogen is down. Just for actually in this case you are seeing that one, but actually this hydrogen is up and this hydrogen is down the plane. So when you have a substituted position, and if you just see when you have a substituted position, it can either be positioned up or it can be positioned like this. So this up position, these are known as your axial. This is axial, and when it is written like this, that is your equatorial. And you will see that the any substituent group when it is present in your equatorial position has lower in energy, or that is more stable. The reason is when it is present in your x, when the substituent is present in your axial position, then it has 1,3 interaction with these hydrogens. The position here, if this is positioned as 1, 2, 3, 4, 5, 6. So this hydrogen is up, that is axial hydrogen. This hydrogen is up, so axial hydrogen. So you have diaxial interaction here, so that would be less stable. Or if you just see the conformational isomer of this one, if we are putting all that in your equatorial position, here you have uh, no steric hindrance in such way. But here if we are putting in your axial condition, so you see here the x and this bond CH2, they are actually gauge condition, not eclipsed, but still it is gauge, and here it is anti-periplanar. So axial conformer is less stable as compared to your equatorial substituent position or conformation at equatorial position. But they are actually interconvertible depending on what kind of your substituents are present. Suppose if you see that in case of methyl, uh, axial and equatorial conformation energy difference is very low, that is 7.3. And in case of your methoxy, the energy difference is as low as 2.5. The reason is in case of methyl, the axial conformation, actually direct interaction is the axial hydrogens of the chain. There is direct interaction with your hydrogen. But in case of methoxy cyclohexane, the methyl group is pointed along this direction. So there is no interaction between your axial hydrogens. And when you have a bulkier group like tertiary butyl, so here you see the energy difference is very high. So here you have a very steady crowding. So the axial isomer, the axial conformer is less stable as compared to your equatorial conformer. So we can just say that whenever we have a monosubstituted cyclohexane, so in that case the substituent goes to your equatorial position preferably. So what about a di-substituted cyclohexane? So di-substituted cyclohexane can have many type of di-substituted cyclohexane. Like we have now, when we have a mono-substituted cyclohexane, suppose we have here, so I'm starting it the number 1, 2, 3, 4, 5, 6. So now 2 and 6 are equivalent, 3 and 5 are equivalent, and 4 are equivalent. So now you can have different position of your substituent. You can have a 1,4 die substitution, 1,4 or 1,2 or 1,3, or okay, you have 3, 1,2, 1,3 and 1,4. You can have this 3 type of die substitution. So first take with your 1,4. So in case of 1,4, again this can be cis or trans. Cis means they are both on the both up or both down. So we know from this cyclohexane, uh, when this one is the actually adjacent positions, so equatorial and axial, they are up, they are up, that means they are on the same side in 1,2 position, or it's equatorial and it's axial, they are on the same side. So in 1,4 cyclohexane diol, when it is your cis, they either can be, one would be equatorial and one would be axial. So there can be, actually these two conformers are same. It can be this one can go up or this can go down. So they are both the hydrogens occupy on the lower side of the ring. Okay. And but in case of trans, one both can be axial or both can be equatorial. So when both can be axial, that would be a actually higher energy situation as compared to when both the conformers are in equatorial position. So that would immediately flip to your di-equatorial position. So in 1,4 cis, one would be axial equatorial, and in trans both would be equatorial. Again, okay, in case of 1,3 cis 1,3, that means both on the same side. Cis means both on the substituent on the same side. They can be again cis, both cis means they can be again both on axial or both on equatorial. So equatorial would be more stable. And trans 1,3, in that case one will be equatorial, one would be axial. Okay, depending on which type of, we will come to it. Suppose you have a bulkier group, then in that case one has to be, bulkier group has to be equatorial, and the less bulkier group has to be your axial. Always bulkier group would be preferably posted in your equatorial position. Okay, when we have your 1,2, in case of 1,2, in case of 1,2, you can have either both equatorial, this one is your trans, this one is your trans, so both can be equatorial or both can be axial. So this one is favored when both are cis. Okay, so one can be axial and one can be equatorial. So here you see you have two different groups. One is bromine, one is your OH. So which one is larger, that will prefer your equatorial position. So in that case bromine is larger as compared to OH, so that will your equatorial position will be occupied by bromine, and your OH group, that is the smaller group, will be occupied by your um, axial position, will be occupied by your smaller group. So when you have three substituents, okay, when you have three substituents, in this case you would see that this isopropyl group is a bulkier group, so that will be placed in your equatorial position, and the rest will be positioned accordingly. So this one is your 1,4 in a if this is 1, this is your 4. So 1,4 position cis, so one would be equatorial, one would be axial. So this one would be equatorial and this one would be your axial, and this OH group would be equatorial. And in this case phenyl and methoxy group. So here you can have either two substituents. You have uh, you have two. In this case, you have two substituents axial, or two substituents, one substituent equatorial, another substituent axial. So here phenyl is more bulkier group, so that would be favored. So similarly, when you have a bulkier group, what I have already told, in that case, that bulkier group will always occupy your equatorial position, whatever be the case. So in this case, the tertiary butyl group is equatorial, but in this case, the tertiary butyl group is equatorial and OH is, because there is no other option. These two are trans, so equatorial will be your preferred position. So axial it cannot be, and in this case one equatorial, one axial. So tertiary butyl group won't go to your equatorial position, axial position. It will always fix your at equatorial position. So next is when you have a double bond. One is your cyclohexanone or methylene cyclohexane. So in that case, you would have a double bond here. So that would be preferred in your actually chair conformation. But when you have a cyclohexene, that means you have a carbon carbon double bond within the ring, then the more preferred conformation is your half chair. Half chair conformation has lowest energy possible. Next, when you have a in cyclohexanone, substituted cyclohexanone, the CH3 group can present at equatorial or at axial position. But in this case, actually the this one is not favored. Actually, the axial CH3 group is favored. That is because of your dipole-dipole interaction. So if it is in your equatorial position, there would be dipole-dipole interaction here. But when it is present in your axial position, that would be in opposite direction. So in that case, there would be less dipole-dipole interaction, and that would be stable. So in case of substituted cyclohexanone, the axial substituent is more preferred. This is also known as your alkyl ketone effect. Next comes your fused rings. Actually, when two rings are fused at two carbon atoms, those are known as your fused rings. So here our two cyclohexane rings are fused, that is known as your decalane. So now this decalane can be fused, means one cyclohexane is fused with another cyclohexane. So this can be done when both the equatorial the other cyclohexane is present at both the equatorial position, or one equatorial, another axial position. So we can have a cis decalane and one trans decalane. In case of your cis decalane, like we know that in 1-2 position, one would be equatorial, one would be axial, then that is your cis. And in 1-2, if both are equatorial or axial, then that would be your trans. So in case of cis decalane, one is your axial substituent, another one is your equatorial, and in case of trans, both are equatorial. Okay, the cis decalane can immediately undergo ring inversion. Like this bond was equatorial axial now, but after some time it would end up in your equatorial bond. So that can undergo ring inversion, rotate, it can flip. But in case of transdecalene, there cannot be any inversion. Actually, we have EA or AE for cis, and for trans we have EE or AA. So for EE you can have this ring, but for AA there would be impossible to join this axial position into your six-membered ring. So for transdecalene there is no ring inversion is possible, but for cis decalene ring inversion is possible because it can undergo from EA to AE. Okay, next comes your substituted decalane. Two examples are there. One is your decalol and decalone. So first, decalone, it can have your transdecalone or cis-decalone. So cis-decalone can have two mirror images which are non-superimposable. So it can have two enantiomers, transdecalone. And in case of cis-decalone, it can undergo flipping. So in that case, these two, it is the mirror image of this. So these two are enantiomers, and these two are enantiomers. So in cis decalone, you get 4 enantiomers, and in trans 1 decalone, you get 2 enantiomers. Similarly, in case of trans 2 decalone, we can have the OH group present in either axial position or in equatorial position, as they cannot get flipped. So in case of trans 2 decalol axial, we get 2 enantiomers, the mirror image of each other, and equatorial mirror image of each other. So you have 4 here. And in case of cis 2 decalol, it can undergo flipping. So either it can give you equatorial axial, or in this case axial equatorial. Again, they would have different mirror images. Okay. So next, your last unit, that is your stereochemistry of molecules without a chiral center. Up to now, we have just discussed that when we have a chiral center, that is a carbon containing 4 different groups, we have optical activity. But there are some molecules where you do not have any chiral center, but still they are optically active. So some of them are your allenes. So in case of allene, allene means you have a carbon, carbon, carbon. So these allenes, actually, if you just see, this one is your sp hybridized carbon, the medium carbon is your sp hybridized. So one pi bond is formed with this carbon atom, and another pi bond is formed on this carbon atom. So these 2 pi bonds are not in plane, actually they are perpendicular to each other, and there is no delocalization of electrons available. So they are 2 mutually perpendicular pi bonds, because this one is, if this is your px and this one is your py, so these orbitals are mutually perpendicular to each other. So in that case, our double bond which is formed, these both pi bonds are perpendicular to each other. So in that case, whenever we put different substituents here, then there is a actually you have a chiral axis. Although they are not actually you don't have chiral centers, but still their mirror images are not superimposable. Suppose you just see these are achiral allenes, which allenes are also achiral, and some are chiral allenes. So which are chirals and which are achiral? You just see this allene where you have actually same substituent. When you have same substituent, you have plane of symmetry along this direction or along your this direction. So you have mirror of plane of symmetry. But when I just uh, change this one carbon and again on that carbon, okay, so in that case there would be no plane of symmetry. So this has in actually mirror image, and these are resolvable, or you can just separate these enantiomers. They form, this exist in 2 different isomers. So chiral allenes must have your different actually substituent groups. So these are your chiral allenes, because there would be no plane of symmetry. So how you assign configurations in allenes? So you have to look it in view it from different directions. So suppose you view it from this direction, and if you are viewing it from this direction, chlorine is on the top and bromine is on the down. So you just put chlorine on top and bromine on down, and then you just see it, your CH3 group is on right, so put it on the right side, and hydrogen on the left side, because you are viewing it from this. So this bond is on top and this bond is on the back. And again here, actually while assigning these notations here, you have to just check you are viewing from which direction, and these groups will first get your first priorities, and the other groups will get lower priority. So in this uh, carbon, we have 2 substituents, bromine and chlorine. So bromine is priority number 1, and this one chlorine is priority number 2. Then we prioritize whether you have bigger groups or smaller groups, but you have to give 3 and 4. Okay, the priorities of the rear end, this is your front end carbon, this is your rear end carbon, those priority will come last. So these 2 substituents from which direction you are seeing, those will get priorities number 1, 2, and this will get priority number 3 and 4. Then you trace from 1 to 2 to 3. If it is clockwise, then that would be R. And here you do not have to check whether the 4th priority is on vertical side or on the wedge, you do not have to check it. You just have to trace the path from 1 to 2 to 3. If it is rotating clockwise, then R. If it is rotating anti-clockwise, it would be S. Suppose you say, I won't view it from this side, I will view it from this side. Again, it is going to give you the same confirmation. If you are going to view it along this direction, so this one is your front carbon. So this is CH3 group is on the left and hydrogen is on your right, and chlorine is again on your right side and bromine on your left side. So now this one will get high priority, and this one priority number 2, and this one will get priority number 3, and this will get priority number 4. And now you again trace the path, it is again going to give you R. So from which direction you are seeing, you are getting the same configuration. So here you have a chiral axis. So this is not because of your any 4 different substituent. Here you are getting a chiral isomer because of a chiral axis. Okay. Uh, Next is spirins. So spirins are in that previous one we have seen fused ring, but here these are not fused ring. Here both the rings are actually joined through a single carbon. In case of fused ring, that is 2 carbons are being shared by 2 rings, but here it is being shared by only 1 carbon. So these are known as your spiro compounds. That is means you are twisting it in between. Because of this spiral actually twisting, you are giving rise to a chiral center actually. So how they are named actually spiro, then actually how many number of carbons are there in your ring. So here you have two carbons, so spiro 2 and total number of carbon is 5, so pentane. So in this case you see you have 2 rings, one is a 3-membered ring, one is a 5-membered ring. So this one is your spiro 2,4 heptane. You have first you have to mention the smaller ring. You have 2 carbons here, and here you have 4 carbons, spiro 2,4, and in total you have 7, so that is spiro 2,4 heptane. And this one is spiro 5,5 on decane, because you have in total 11 carbons, so that is on decane. And on both the rings you have 5 carbons except this your common carbon, so that is spiro 5,5 carbons, spiro 5,5 on decane. This spiro compounds, whenever you do not have any substituent present there, you have a actually a plane of symmetry. But when you have different substituents, then it causes axial chirality, because you have a chiral axis. Suppose you have different substituents and these molecules are named, or they assign your absolute configuration as you have assigned in your allenes. So here I am viewing it from this side. So NH2, this one is my front carbon from front side. So NH2 on top and hydrogen bottom. And when I am viewing it from this side, NH2 is on the left side and this hydrogen is on your right side. So NH2 on the left side, hydrogen on the right side. And then assign the actually prioritize them, give the priority. In this carbon, this one is having higher priority, this one is having lower priority, and on this side it is higher, this is lower. So this will be 3, this one would be 4, and you would have a R configuration. Next, also you could have alkylidine cycloalkanes. So alkylidine cycloalkanes are nothing but your like your alene compounds. You have just substituted a cycloalkane ring in place of a double bond. So alkylidine cycloalkanes are also your can exist in different enantiomers, and they are resolvable. Resolvable means you can just actually separate them, or you can have different isomers if you have different substituents present there. So you can also actually assign configurations to this one. Suppose for this one I am viewing it from this side. So my COH group is on the top, hydrogen bottom. So when I am viewing it from this side, CH3 is on the left and hydrogen is on the right. So in this carbon I have this 1, 2, and this one is 3, this one is 4. So 1, 2, 3, 4. So that would give me R. Okay. But this one is going to give me S. Suppose you can just see it from this side. 1, 2. This one is 3, 4. COH, H, and H is on the left, CH3 is on the right. So this is 1, 2, 3. So that is your anti-clockwise. So that is going to give you S, and that one is your R. So you can just assign your configurations to alkylidins, cycloalkanes, as you have done in case of your allenes. So their actually mirror images are not superimposable with each other, so they exist as your enantiomers. Okay, so these are the actually molecules which show chirality due to axis, or these have your axis of chirality. These have axis of chirality. Next comes your biphenyls. Here you do not have a chiral axis, but still you have some stereochemistry in biphenyls, because biphenyls means you have two phenyl rings joined by, means this carbon of this phenyl and this carbon of this phenyl, they are joined together. So actually when you do not have any bulkier groups here, they are quite, you can just rotate it through this carbon carbon bond. But when you have bulkier groups, there would be possibility of steric hindrance, so they won't be rotated, they would be fixed in a particular position. So like in this case, so now it is difficult to rotate this bond because there would be steric hindrance, so it would be have different isomers. So this type of isomerism, which is resulted because of the restricted rotation about the bond linking the two phenyl ring due to steric hindrance between the bulky orthosubstituents, is known as your atrope isomerism. Normal biphenyls, they do not show actually stereoisomers, or they do not have stereoisomers because they can be rotated easily. But when they have bulkier groups at the ortho positions, so that is there is difficulty in rotation. So this enantiomer cannot be rotated to give this enantiomer. So once this is formed, you cannot go back to that the other isomer. So they can be resolved. Okay, so this type of isomerism is known as your atrope isomerism, and these isomers are known as your atrope isomers. So sometimes each ring, there are some conditions. Each ring must be unsymmetrically substituted, and both rings must be substituted in ortho position, and the substituents must have a larger size. The smaller size hochi matya, in that case also they cannot be resolved. They can actually rotate to give the other enantiomer. So it is you will always get a racemic mixture actually. But when you have bigger groups at your ortho position, it is difficult to rotate them. So you can resolve them, means you can just separate the enantiomers one formula. So in this case also you can assign the notation as we have done in case of allene. So if you are viewing from this side, nitrate is nitro group is on the top, and uh, carboxyl group is on the bottom. As you know that NO2, nitrogen, is having more atomic number as compared to carbon. So this one will get first priority and this one will get second priority. And in this case, actually when we are viewing from this side, they will get top priorities and this will get the other priorities 3 and 4. So in that case you are getting a ace enantiomer 1 2 2 2 3. Next is you have a buttressing effect. In buttressing effect, suppose you have uh, actually in this case, okay, 2 prime bis trifluoromethyl biphenyl. In this case, you do not have many bigger groups here, so this can be easily rotated. So its enantiomer is actually you can go back to its enantiomer. So you would have a equilibrium, and here there you can have both the enantiomers present in your mixture. But when you put a C2H5 at your meta position, so in that case, that actually what happens, it increases the steric repulsion between the ortho substituent when you put a substituent at your meta position. So the energy barrier for racemization actually increases. So in that case, that won't racemize, or you can just resolute its enantiomers or separate the enantiomers. It won't decimize. Actually, we know that from one enantiomer, when we are just rotating it, you can get the other enantiomer. So in this case, when you are putting a bulkier group at your meta position, the rotation is not possible. So in that case, your decimization does not occur. So there is another type of, okay, cyclophanes are also there. So in that case, you have a plane of chirality. Plane of chiral cyclophanes are like you have two aromatic rings and they are joined by carbon chains where your M and N can be up to 4. After 4, you won't have a chiral plane. But even when M and N are 4, the compound cannot be resolved, like they racemize. But when you have less than 4, they can be resolved. Like you can just see here, 2,2-paracyclophane carboxylic acid, these are resolved. But here you should have a substituent. Even our ferrocin, that is also chiral when you have a substituent there. And so these are known as your molecules with chiral plane. You do not have a, so that plane is chiral, we can just say. And again, there are some ANSA compounds. In ANSA compounds, as we are having here two phenyl rings, in case of ANSA compounds, that is also a cyclophane, but here we have only phenyl ring and we have a carbon chain where CH2 is CH2 whole N. So you can have, you see, many different conditions, but when Y is equal to H and N equal to 10, so in that case, it is non-resolvable because they can interconvert or they can undergo racemization to give the other enantiomer. So optical activity disappears in that case. But in other cases or some other conditions are there. So in that case, you have high energy barrier to rotation, so you can resolve the compounds or you can get a pure enantiomer without resolving. They don't undergo rotation, so it would be non-resolvable. Resolvable, sorry. Next is there is some helicity. I have not put it in your slides. Okay, chirality due to your helicity, like your helicin. These are your hexahelicin. So you have, you cannot, like this mirror image, you cannot turn it to get its mirror image the other enantiomer because of your steric interaction between the terminal rings. These terminal rings have steric interaction, so you cannot just rotate it or flip it to get the other its other enantiomer. So this show a chirality. So in case of your trans-cyclooctane also, it is difficult to actually flip it. So they show two different enantiomers. That is your trans-cyclooctane. Next is your cyclostereoisomerism. So cyclostereoisomerism means in cyclic compounds we have stereoisomerism. Suppose you just see in case of your 1-bromocyclopropane. So in that case, here you have a plane of symmetry. Okay, so this, although you have a chiral center here, you have 4 different groups here. Okay, you have 4 different groups here, but still this is a chiral molecule because you have a plane of symmetry passing through this. In case of this either trans or cis isomers, okay, disubstituted cyclohexane, trans or cis, they are also achiral, which I have already shown you. Like whether it is a cis, there is a plane of symmetry here. This one is exactly half of the other one, and whether it is a cis also, you have a trans. So here also you have a plane of symmetry. So they are achiral. But what about this one? When you have disubstituted, they are present in your mirror forms. So they both are non-superimposable. So these two are enantiomers. Even this trisubstituted cyclohexane is also present in your enantiomeric forms. Next, this one is your adamantine. Stereochemistry of adamantine. Adamantine is like your, actually it is showing 4, but actually 3 cyclohexanes are fused together. So if you just see the center of this carbon, so it is attached to it, looks like it is attached to four different substituents. So it is nothing but a chiral carbon, how we are having four different substituents. So here we do not have a chiral center, chiral carbon, but we have a chiral point. Okay, so you are having when you have four different substituent, only adamantine is not your optically active, but when you have three different substituents present at these positions, that behave as chiral. So you just see this, this is your tetra substituted adamantine derivatives, you have enantiomers. Okay, even your disubstituted derivatives, in this case also you have your enantiomers. So here they do not feature a chiral center but an axis of chirality, or in this case you have an axis of chirality, but in this case you have a point chirality. Okay, so in this case you have a axis of chirality, as in case of your allenes. Okay, I think I have covered all the four units. Just some are remaining, which I have just kept. Like in your unit 2, you have like stereo isomerism for molecules with three or more chiral centers, and pseudo asymmetry. Actually, that again come in your unit 6. So I have kept it for that unit, for pseudo asymmetry and compounds or your molecules with three or more chiral centers. Okay, so we will discuss it in our next class, that is tomorrow, that is in your unit 6. So I am not repeating there. And again we can also repeat the RS notation. Actually that is tomorrow also in your unit 5. I think you have that RS notation and EZ notation. So there all we can again just refresh those, and we can just move on to other things like your there you have, I think, RS notation. Then how would be the reactivities depending on your environment, some rules, and some other things are there. You can just we can just discuss it tomorrow. So if you have any doubt in today's class, you can just ask me. We can now discuss about that. Anyone is having any doubt? Anyone is having any doubt, we can just clarify.
ମ୍ୟାମ୍ ଆଲିନ୍ସଟା ଆଉଥରେ ଟିକେ
Alliance ଟା ଟିକେ okay.
ଖାଲି ଟିକେ ଓଭରାଲି ଟିକେ
ହଁ ହଁ, no problem. ମୁଁ ଯଦି first ହେଇଯାଉଛି, you can just tell me, because I have to means finish a lot of things, and this is my first class actually. I have never taken this classes for so long. Okay, allines actually we have two carbon-carbon double bonds, and they are not in conjugation. They are actually one carbon is having two double bonds to its uh, adjacent carbons. So the central carbon is actually sp hybridized, and so if we have a so it has a px orbital and a py orbital. So its py orbital and this py orbital are overlapping to form a pi bond, and this its px and its px are overlapping to form a pi bond here. So as px and py orbitals, we know that they're mutually perpendicular. So these two pi bonds are mutually perpendicular. So here when we do not have any substituents, we still have a mirror planes. Okay, we have mirror planes, but when we do not have means substituents, or when we have substituents but they are same substituents or having hydrogen hydrogen or same substituent, in that case this mirror plane will have a plane of symmetry, either this one or this one. But when I just change this substituent to a other group, Okay, in that case, we do not have a plane of symmetry. Okay, as we do not have a plane of symmetry, so in that case, although we do not have a chiral carbon, means a carbon containing four different substituents, but in this
Substitution.
case, we do not have actually a plane of symmetry, but we have a C2 axis. Okay, we have a C2 axis. But still we know that this molecule is not asymmetric as we are having a C2 symmetry. So these molecules are actually disymmetric. Okay. Asymmetric when it will have asymmetric when you have no plane of symmetry, no rotational symmetry. But here we do not have a plane of symmetry or any our alternating axis of symmetry. So for that reason, we can say that these molecules, when you have different substituents, okay, so it should be chiral, but it, or we can just say it shows optical isomerism. So in that case, you see when these two chlorine chlorines are there, so in that case we have a plane of symmetry also, actually starting from this is your cs3 group, and we can have a plane of symmetry here. So this is also not optically active. So this, for this we have to have two different substituents here. So you বুঝা পড়লা তো? This is
ଆଜ୍ଞା ଆଜ୍ଞା
symmetric not because of your this is sorry, this is chiral because you do not have a plane of symmetry here. Okay, the plane of symmetry 9, so this is a disymmetry molecule. Here you have a chiral axis. This axis is your chiral axis. So when assigning configuration in case of alkenes or spiro compounds or your biphenyls, you have to check from which side you are viewing. If you are viewing from this side, your chlorine is on top and bromine is on down.
ଆଜ୍ଞା
Kona?
ଏଇଟା ଟିକେ ବୁଝେଇଲାନି ଯୋଉଟା
କୋଉଟା ଏ କନଫିଗରେସନ ତ?
ଆଜ୍ଞା ଆଜ୍ଞା
ହଁ, ତେଣୁ ତମେ ଯୋଉ ସାଇଡ୍ ରୁ ଦେଖୁଛ ହେଲା, ତମେ ବର୍ତ୍ତମାନ ସପୋଜ ଯୋଉଠି ଆଖିଟା ଅଛି ଦେଖ ସେଇ ସାଇଡ୍ ରୁ ଦେଖୁଛ, ସେଇ ସାଇଡ୍ ରୁ ଦେଖିଲା ବେଳକୁ ଏଇ ଡିରେକ୍ସନରେ ଯିବ। ଏଠି ତମେ ଏ କାର୍ବନକୁ ଆଉ ଭାବିବନି। ଓକେ, ୟୁ ଜଷ୍ଟ ସି ଦ୍ୟାଟ୍ ଇଟ୍ ଇଜ ଏ thing which is having four different substituent. Okay, so from this, when you are viewing from this side, chlorine is in top and bromine is down. Okay, just put it, chlorine is on top, bromine is on down. And from viewing this side, hydrogen is on the left side. Okay, hydrogen is on your left side and cs3 is on your right side. Okay, next comes your giving priorities. So when in case of alkenes or whichever this chiral axis having stereoisomers having chiral axis, in that case you do not give the priorities as a whole. You just put first priority from those substituents which are just in front. So these two substituents are in front. So among this, bromine is having higher priority, chlorine is having lower priority. So put bromine 1 and chlorine is your 2. And then comes your priority of the rear end carbons. So substituents on the rear end. So in this rear end, we have CS3 group and hydrogen. So among these two, CS3 is having higher priority as compared to hydrogen. So this will come as 3, this will come as 4. ବୁଝିପାରିଲେ ତ? ଯୋଉଟା ତମର ଫ୍ରଣ୍ଟ ରେ ଅଛି ତାକୁ ଆମେ ପ୍ରାୟୋରିଟି ସବୁଠୁ ଅଧିକ ଦବା. So that will come as 1 and 2. ଓକେ, ସେ ଯାହା ବି ଥାଉ, ଏଠି ମୋର ହାଇଡ୍ରୋଜେନ ଥିଲେ ବି ମୁଁ ତାକୁ 2 ଦେଇଥାନ୍ତି। ଓକେ, ସେ ଯାହା ବି ଥାଉ, I will give it as 1 2 and the rear end କୁ ଆମେ 3 4 ଦବା, ପୁଣି 3 4 ଦବା depending on their priority. So now we can just trace the path from which direction it is going. From 1 to, always you just trace the path from 1 to 2 to 3. Okay, so while going from 1 to 2 to 3, in this case it is which direction?
clockwise
1 to 2 to 3 clockwise. So this has to be R. Okay.
okay again
Whenever you have hydrogen or whatever, so just see here we have hydrogen. Okay, so this we are viewing from this side and we have NH2 group, so hydrogen will be given priority number 2 and this hydrogen will be given priority number 3 and this hydrogen will be given priority number 4. Okay, then you have to do it like this. In all these compounds we have to assign the configuration like this only, and in this case you just remember you don't have to put the fourth priority in wedge or in your vertical way. So it has to be as it is. You just assign the configuration whether it is clockwise or anti-clockwise. But when we are doing for the stereogenic centers or for your that chiral carbons which we have already discussed, when you have your tetrahedral carbon, in that case if your hydrogen is on the horizontal side, then whatever configuration you are having, then you have to just reverse it. Okay.
Yes. Again.
How kichi doubt ache? Actually stereochemistry you have to do lots of imagination and you have to do
Madam,
it
এটা
with
3D madam, এটা 3D ର ଜ୍ଞାନ ନଥିଲେ କିଛି ହେଇପାରିବନି।
that's true. So you have to actually imagine yourself, means you have to
ଇମାଜିନ କଲା ବେଳକୁ କ୍ଲାସ
model.
ସରିଯାଇଯିବ।
That actually that's true, but you have to do it through the. Actually, I could use the models, but in that case, it will take me very long actually. So, yeah. Okay. So, anyone else is having any doubt? Okay. Okay, can come prepared tomorrow for unit 5, 6, 7, 8, or whatever doubt you are having for today's class. We can also discuss tomorrow. Okay, and you should come prepared. Go.
मैडम तार पीपीटी टा मैडम टिके शेयर कर दियंती।
पीपीटी शेयर करिवे एटा तो तमर सब अछि मो टिके जस्ट अलगा जगह रो अल्प अल्प आनी छी तमर सब तक अछि जदी देखिए कोतरे शेयर करिवे आई डोंट नो एक्चुअली
मैडम
आई हैव नो आईडिया
जणन को काहू के शेयर कर देले भी हमर ग्रुप रे।
ओके आई विल लेट यू नो टुमारो
ओके ओके मैडम।
because actually you can get it in your material. You are having everything. I have just taken something from the internet or somewhere, and also you can just actually go through your NPTEL lectures. Okay, NPTEL lectures YouTube. Actually, Amit K Basak, someone is from IIT Kharagpur. He has actually around 40 to 40 lectures he is having for on stereochemistry only, but he has not covered also all the stereochemistry, but he has explained very nicely. So you can go through those actually videos also if you are more interested.
Ma'am,
Okay,
repeat, ma'am.
Go there.
YouTube class, ma'am, YouTube class कौन कहले आपको?
हाँ सेटा NPTEL रो NPTEL lecture NPTEL. Okay, NPTEL lectures तमे मार दबो stereochemistry NPTEL lectures Google रे मार दियो, you can get lots of videos. Okay, from NPTEL. Okay.
हाँ मैम।
हाँ
Stereochemistry class, ma'am.
हाँ stereochemistry, you can just put stereochemistry NPTEL lectures or reactive intermediates NPTEL lectures. You will get most of the things from there actually. And your material is also good. You can just go through those also.
हाँ मैम। Material तो हम पाखे भी नहीं, तो सेटा में बेसी problem होची।
Material तो you can download it from the internet ना.
हाँ, e-content book तो देखी होची, but soft copy, hard copy नहीं तो से में टिके problem होची।
अच्छा अच्छा सब किन सेट्रु भी देखि परिबो माने भल देखि दबो सेट्रु सब तक मटेरियल मिल जाउत सेतरे आमे तो सेट्रु प्रैक्टिस एक्चुअली करू so you can go through those also. Anyone else is having any doubt? Okay, so if no one is having any doubt, then we can just stop here. Okay, end our class, today's class here. Or if anyone is having any doubt. I hope everyone understood something. Okay, we will continue tomorrow at 6 o'clock then. With any, any doubt?
Thank you, madam. Thank you, madam.
Okay, okay, most welcome. Okay, yeah, okay, okay, that's for today. Okay.